Today we are going to finish up our second exponential and logarithmic equations. So we looked at just solving the exponential equations. So today we are going to solve logarithmic equations, and also we're going to add a real life problem that involves either a logarithmic equation or an exponential equation that would involve using logs to solve it. So in order to solve logarithmic equations, we're going to do one of two things, and again it just depends on the situation, but we may use the swoop method. You may have to simplify using some of your properties first before you swoop. This is going to seem new, and when I describe it, it's going to seem complicated just because it's got the base b, x, and y, but there's a property that if log base b of x equals log base b of y, meaning that if it's a logarithm with the same base of two different things, that we can just drop the logs and set the quantities equal. So if we have single logs with the same base on both sides of the equals, we can simply just set the quantities equal to each other and then solve. So that should be pretty easy. Now we will have to check here for extraneous solutions, so make sure that once we get an answer, that we check it to make sure that it works. So after you've done one of the two above, we may have to use a variety of different equation solving methods. So you might be left with something that is linear, which is super easy to solve, but it might be quadratic, which means we might need to factor or use the quadratic formula. If it's something that's higher than a quadratic degree, if we have a cubic or a quartic, remember that those ones are almost always going to be factorable for you. So once you have your answer, you need to check to make sure it's not extraneous. Like I said, you don't need to press the whole problem into your calculator. The only thing that we cannot have with extraneous solutions is that you can't have, so it doesn't give you the log or natural log of a negative. So all you have to do is plug it into anything that has a log on it and make sure it's not going to give you log of a negative, because that would be undefined. Okay, so let's look at example 1a here. Solve the equation, check for extraneous solutions. So this one we just have a single log, and if we look, we've got both individual sides as simplified as they could be. There's nothing else I can do here. X and 3 aren't like terms. Obviously, it's just a 2 on the right side. So that means here, all we're going to do is to swoop. So start with our base. 4 to the second power equals x plus 3. So 4 to the second power equals x plus 3. It's magical because now our log is gone, makes it very easy for us to solve. So simplify your 4 squared to 16. So if 16 equals x plus 3, then we subtract the 3 on both sides, and we get x equals 13. Now, I need to check, make sure that it's not going to give me a log of a negative. So I put the 13 back in on the side that has a log. 13 plus 3 would be 16, and that does not give me a log of a negative. So we are good there. X equals 13 is a valid solution. All right, so let's look at B. B is a little bit different because we have a log on both sides. So when we have this is very similar to what we did with radical equations. If you would happen to have two on the same side, then you would need to move them to opposite sides. Once we have them on opposite sides, because the bases match, that means we can just drop the logs. So bases match, which means we're going to drop the logs. So that just leaves us with 2x plus 9 equals x plus 4. Again, very easy equation to solve. So I need to get my x's to one side, my numbers to the other. So subtract x, subtract x. So that gives me x plus 9 equals 4. So subtract 9, x equals -5. So I'm going to take that and I'm going to try it and make sure it doesn't give me a log of a negative. So in here I've got 2 times -5, which is -10, plus 9, which is -1. Log base 2 of -1 can't take a log of a negative, so this is extraneous, and since it was my only answer, that means that the answer here for our final is no solution. All right, I would like for you to try C and pause it for a second while you try that. Shouldn't take you too long, and then unpause so you can check your answer and see if you got it right. Okay, so this one is very similar to B. We have log base 4 on both sides, so that means we are just going to drop the logs off. So that gives me x plus 3 equals 8x plus 17. So solve for x. I'm going to get all my x's to one side. So subtract x. That gives me 7x plus 17 equals 3. So subtract the 17. 3 minus my 17 gives me -14. So -14 equals 7x. Divide by 7, and I get x equals -2. So now I'm going to plug it in and check it. -2 plus 3 is +1, so we're good on that side. Check over here. 8 times -2 is -16, plus 17 is also +1. So this checks out, and we are good to go there. All right, last one. I would also like for you to try this one, but I will give you one hint first. We need to get the logarithm term all by itself. So get this by itself first, and then because it's just a single logarithm, we're going to have to swoop. So see what you can do on this one, and then unpause it to check to see how you did. So first thing we would do to get the log by itself is subtract 7. So that gives me 2 natural log of the opposite of x equals 7. Then I need to divide by 2 on both sides. This doesn't come out evenly, so leave it as a fraction. I've got natural log of the opposite of x equals 7/2. So now if I want to solve, that means I need to swoop. So the base here, remember, is always e for a natural log. So when I swoop towards the equals, e to the 7/2 power equals the opposite of x. So to get x alone, all I would need to do here is divide by -1. Well, when you divide by -1, that just changes the sign. So I've got opposite of e to the 7/2 is what x is equal to. So we need to plug that in and check. So if I plug that into the log, the opposite of -e to the 7/2 would be positive e to the 7/2. So that does not give me a log of a negative. So that means that this is complete and is a solution. So -e to the 7/2. All right, so hopefully you find those pretty simple with solving the logarithmic equations. Now we're going to look at an example that uses an e, which uses logarithms and exponentials here. Newton's law of cooling. It finds the temperature of a cooling substance using the equation. So if you know the initial temperature of the substance, as well as the room temperature, then R is the cooling rate of the substance. So we're going to be using this formula. Notice all the different variables. It tells you what they stand for. Notice that we've got an E here as well. So it says you are making soup that is 212 degrees Fahrenheit when you take it off the stove. If the room temperature is 70 degrees Fahrenheit and the cooling rate of the soup is 0.046, How long will it take to cool the soup to a serving temperature of 90 degrees Fahrenheit? Obviously, you don't want to burn people if you're a restaurant and trying to serve soup. You want it to be hot, but you don't want it to burn anyone. So, if when you make it, it's 212. 212, when you take it off the stove, that's the initial temperature. So that means that has told me that T sub O is 212. The room temperature is 70 degrees Fahrenheit. That's important because T sub R, they told me now, is 70. The cooling rate of the soup is R equals 0.046, so 4.6%. So that one's pretty easy. We can just copy it how it is. That's my R. How long will it take to cool the soup to a serving temperature of 90 degrees Fahrenheit? So the temperature T, we want it to be 90 degrees. So the only thing we don't know here, if you look at our formula, we want T to be 90. We know T sub O. We know T sub R. E is obviously just the number E. We know R. We don't know this little t. And here's T sub R again. So the only thing we don't know is this, which is time. How long? So that's what we're going to be solving for. So we are trying to find small t. So we need to plug in what we know into our formula. So 90 equals, parenthesis, T sub 0 is 212, minus T sub R, which is 70, times E to the negative 0.046 T, so remember that's what I don't know, plus T sub R, which again is 70. So that goes in two different places. All right, so to solve this, we first need to subtract 70 on both sides. Gives me 20 over here. Then if I do the 212, take away the 70, that gives me 142. So 142 e to the negative 0.046 t. So if I'm trying to get t alone, I need to divide by 142. So 20 divided by 142 gives me 0.1408, and that is equal to e to the negative 0.046 t. Now, we had solved these before where we kind of guessed and checked, but now we know how to solve this. We learned this in 8.6 Part A, so now it's time to apply it. When I need to get a variable down from the exponent tower, the opposite of an exponential is a logarithm. So I need to take the log of appropriate base on both sides. So remember, the appropriate base log is whatever the base of the exponential is. So I need the log with base e, which of course is the natural log. So natural log on this side, natural log on this side. When I do that, remember, because the base of the natural log is e and the base of this exponent is e, we can apply the property where when the bases match, the log and bases cancel out. So natural log of 0.1408, I can actually type that into my calculator. So type in ln 0.1408. Hopefully you get negative 1.96, and again the log and the bases canceled out over here, so I've got that equal to negative 0.046 t. So now all I have left to do is divide. So divide both sides by negative 0.046, and you should get t is approximately 42.6. And so since we're talking about time and it's in minutes, we'll just round that to the nearest minute. So we're going to say that it's going to take 43 minutes to cool from 212 to 90 if room temperature is 70 degrees. All right, that is it for this lesson.